Good day, my name is Jamil Gafur, and we are going to talk about the summer project, Non-Equilibrium Molecular Simulation of Polymers Under Flow, more specifically my part, saving energy through process optimization. This was worked on in collaboration with Dr. Lin Talbu and Dr. Michael Crowley at the Renewable Energy Lab in the Renewable Resource and Enabling Science Center. Now, in order for us to begin, we should talk a little bit about the background. So the background of this project is essentially the study of plastic extrusion to minimize the buildup of plastic around the extrusion pipe. So, for example, given this image in the upper right-hand corner, we have plastic beads that are fed into the hopper, then heated and pushed out of a feed pipe or mold using a screw. If we have buildup starting to occur around the feed pipe, the overall product's structure and stability is decreased significantly. For example, if we look at the printing of a cylindric tube and we get a top-down view as such, we have the feed pipe represented here as the outer ring and then the actual plastic being pushed out of it. The speed of the plastic is represented by the color, where blue is slow and red is faster. So, if we look at the boundary condition, which is the polymers between the pipe and the plastic, you have something called laminar flow, where the plastic moves slower. This can be for a whole bunch of different reasons, from friction, different temperatures, or stuff like that. On the other hand, as you move inward, you have plug flow or flow velocity, and that is where the polymers are moving at a normal speed. In this case, you have a speed distribution or a speed gradient. Now, because of this, you have a molecular weight distribution. So the molecular weight distribution is where you have longer molecule chains moving inward while shorter molecular chains are moving outwards. So with this being said, the impact of this study is to strengthen U.S. companies' competitiveness in the open market, as well as research emerging molecular simulation techniques. Our work for this summer is to take the existing code and set up a framework for future development and integration. So now that we understand the project, let's go into what we've done so far. Previously, before coming onto this project, users were given a zip file of Fortran 90 code with an example simulation script that the person can modify for their work. On top of that, there was only one file that had a couple lines of documentation on how the code works, as well as how to use it. To date, this code is being used in many projects with a long runtime, some simulations lasting up to 6 months. On one hand, we have people saying, if it works, don't fix it. But we believe that if we fix this framework, we can make it easier and more optimized for future users and encourage people to research and develop more into this. Now, this is being done, hopefully, by setting up certain research software engineering practices like continuous integration, unit testing, documentation, and all of that fun stuff. So in order for us to begin, our first steps, of course, was to set up version control. We did this using GitHub, and then we added a whole bunch of other information associated with the repo, such as different timelines, milestones, short-term and long-term goals. From there, we added a whole bunch of documentation on how to get the code, how to set it up, even different repositories that might be useful to use later on. After that, we had a nice foundation for moving forward. However, there were no forms of test involved. So we decided to implement some form of unit testing so future developers can have a certain sense of certainty represented with their code. But I don't know enough about polymer physics in order to write unit tests. So, since we had a previous example simulation, we ran that simulation, saved the output files, and for future development, we compare the output of that simulation to this golden set. While this is not the best way of going about it, because of it, I've had a little quote that I've made. I have the same level of confidence that this code works now as when I got it, even though I am pretty sure something is messed up somewhere. Moving forward, we hope to implement unit testing, but for now, this is the best that we can do within the SUML. So now that we have the repository set up, and when we make changes to the code, we can have some level of confidence that we didn't break something, let's look into actually optimizing the code. So in order for us to optimize the code, we used Intel's profiler called vtune to see exactly where bottlenecks are occurring inside the code. So when we looked at it, we had this little summary developed. 88.6% of the time, we were doing computations. We had no MPI or threading done because we didn't implement that yet. And then the rest of the time was spent on writing files to the output. Now this application was very compute bound. We had to figure out a way of optimizing the code to get some speed up out of it. Our first thought was using multi-threading. However, that didn't work too well. So if we looked at the actual subroutines inside of the code, we saw most of the time was being spent in our velocity, chain calc, and box calc submodules. So let's zoom in a little more into the first one, which would be the velocity subroutine. Looking at the velocity subroutine, most of the time was spent in these 4 if statements. And this makes sense because the velocity calculates Monte Carlo runs. Using Monte Carlo, every particle would have to go through this subroutine multiple times. So how do we go about optimizing these codes? Well, if you're a little understood in computer science, you can see there's not a lot of ways to optimize this. So we moved forward and looked at different codes, but we found out most of the issues were due to memory allocation. So, as previously shown, the code is very computational heavy, and we have a lot of issues with memory allocation and logic. This is hard to parallelize or even optimize in any form. But who said life was easy? The goal of science is to move forward as best we can and push past the boundaries we set on ourselves to explore and document the unknown. So how did we explore this unknown? After some back and forth with our mentors, we decided to come across a really fancy way of solving this problem. So if we zoom in on this one subroutine for the Monte Carlo moves, we see that it took up about 20% of the compute time. So we're going to zoom in on the first if statement. If the displacement, or D, is 5, 7, 9, or 12, we increment the Y array by 1. So what we ended up doing is using bitmask. Well, first we had a randomly assigned integer that represented D, where the binary bit of D, in this case 5, was 1. So now that this is done, what we ended up doing next is creating a new variable, which is a 16-bit integer that had the if statement's values 5, 7, 9, or 12 initialized. So we can see here in this integer class in blue that the 5, 7, 9, and 12 bits are turning to 1. And this is representative as 2384. Now Fortran has this really cool thing called intrinsic AND, which treats these bits or these integers as a truth table. So if we combine the two and use an intrinsic AND, where the overlap is going to be where the 1 is initialized. In this case, we have the yellow value of D in the 5th location, and then you have the integer that's been represented in blue with 5, 7, 9, or 12. So when we use the intrinsic AND, only 5 is going to have the 1 bit implemented. Everything else is 0. Now that we also know what that D representative is, in this case 5 minus 1, it's just 4, we can shove everything down 4 bits. And that'll give us a binary bit of 1 in the ones place, which is what we want to increment by. So now we've condensed our if statement from 20 or more clock cycles down to 2 clock cycles by using intrinsic and I shift. So the code goes from looking at this if statement above all the way down to just 2 computations at the bottom. So does this work? Is it working well? Well, by using the vTune profiler from Intel, we were able to see how much runtime is actually being saved. We have the original non-optimized code that had output which ran a little bit less than 100 seconds. From there, we optimized it using the G-Fortran flag, and then we looked at that and compared it to our updated code where we changed the if statements to our new statements. And then we did a couple of different permutations of that with and without the output. Now, looking at all of this, we saw the most speed up, thankfully, when we had our updated code that is optimized using the G-Fortran code and had no output, which is what we expected. So woo, we did it. Congrats. In conclusion, by implementing certain parts of the algorithm to be more memory aware, we can get a runtime speedup. And then, looking at the code, sometimes fixing the code is better than implementing parallelization, because when you implement parallelization, you get some overhead. For example, in this top image, you can have an array, a 3-dimensional arrays all initialized to 0 by going through each point and setting them to 0. Using parallelism, using OpenMP, we can do that. However, the most optimal way is just to set them initial to 0, which is being done by the G-Fortran compiler automatically. So the algorithm is just as important as the hardware. And as we've seen, by changing the algorithm, we can get a good speed up. Thank you for your time. That's it for today. And if you have any other interests or questions, feel free to message me. My website is shown here. Have a wonderful day.